Okay, molar concentration, there's the title there, pretty straightforward. And a definition of it. You don't need to rewrite molar concentration, but you can write molarity. That's another way to say molar concentration. Now the term molar there, I'm pretty sure it's spelled exactly like the big teeth at the back of your mouth. But it just simply means pertaining to the mole. And again, just like we had yesterday, our concentration unit comes down to the amount of solute in a particular volume. And in this case now, it's moles of solute in volume, which is in liters. And it has to be in liters because that's what it's defined as. It's how many moles are in a liter of solution. Now here I've got an equation, and this is going to be a very important equation to us. And you can see here we've got C subscript capital M. That represents molar concentration. And then that's equal to N, which is the number of moles over V. And I'll just complete these units here. So N, and why is my pen not working? Let's try that again. So N is moles, all right? Obviously in unit moles. And V has to be in liters. And in terms of the concentration unit that we get, it's a little confusing because we do have a symbol that represents moles divided by liters. It is often written as a capital M. So when you see capital M, you need to think molar concentration. But it's far more convenient to think of it in terms of the units we've just defined there, which is moles per liter. So I'm going to be using both units. And if I give you a number that has a unit capital M, I'm going to suggest that as soon as you get it, rewrite it as moles per liter. Because when we rewrite it as moles per liter, it's then in a configuration that we can use as a conversion factor. All right. To begin, we're going to just practice calculating concentrations, and then we're going to use the concentration number as a conversion factor. So just to start, some straightforward examples. Now, under normal circumstances, we're either, given a conversion factor and have to convert something, or we very rarely need to find the conversion factor. Now, molar concentration is a conversion factor itself. And so I suggest to you that if you're asked to find molar concentration, I want you to write down C equals N over V. That's the very first thing that I want you to write. So the question asks, determine the molar concentration. This is one of those indoctrination things, just like molar mass, just like, what's the first thing we need for stoichiometry? Balanced chemical equation. If it asks, what's the molar concentration? Write C equals N over V, all right? Because sometimes they're going to just give us the numbers and we put it in the equation, but other times we might have to go searching for the N. Like I might be given grams, and then I've got to convert it to moles, and then I'm going to stick it in. So this gives us kind of a plan on what to do. At this point, you can see we've got the number moles. We just have to put it in, 0.232 moles. You don't have to put S on the end, mole. And now we need that volume, and the volume must always be in liters. And now this is a conversion that we will be doing over and over and over again. We need to convert the milliliters to liters. Now you can use our little table that we've got back there, and I'm not suggesting you write this down every time, But if I have 250 milliliters, then I can switch that 250, I can switch the milli for times 10 to the minus 3. And that becomes kind of an ugly thing. That is exactly true. You could put 250 times 10 to the minus 3, but whenever you've got times 10 to the minus 3, what ends up having to be done is you're going to move the decimal place to the left 3 spaces, because you're making it times 10 to the minus 3. It's like you're dividing by 1,000, or you're multiplying it by 1,000th. All right? So I really suggest that you just get into the groove of moving that decimal place over 0.250 liters. So it does come from what I've shown you in the past, but this is one that you're going to use over and over again. There's 1,000 milliliters in a liter. So if you want to turn those milliliters into liters, you got to divide it by 1,000. You got to divide off that 1,000. So you're moving it to the left 3 spaces. So now we've got 0.250 liters, and I'm hoping someone has been calculating as I've been waiting. What do you got, Bradley? That's correct. Are you talking about in terms of the volume of the solution itself? We have to make an assumption that the moles will dissolve completely into the liters and not result in a volume change. Or a better way of thinking of it is that we dilute it up to 250 milliliters. We put the mass, the solid, into a beaker, or not a beaker wouldn't be a very good way of measuring, perhaps a graduated cylinder, a large one, and then we add water until we get to 250 milliliters, and then we mix it. All right? Would there be a practical volume change? Sometimes there is. It depends on what the solute is. Some solutes will actually cause the volume to get a little less. Some solutes will cause it to get a little more. Some solutes don't even have an effect on it. But we're not going to address that here. That would be too confusing. So we're just going to assume it's diluted up to 250 milliliters. Okay? All right. What do we have for a number? Somebody got something? Yep. 0.928 moles per liter. You could put a capital M there, but I suggest when you're doing calculations or when you're dealing with molar concentration, write it as moles per liter. Because in a moment we're going to use it as a conversion factor, and you're going to have moles per 1 liter, and that's going to allow you to flip around and do various conversions. Now that one was the straight up easy one to start with, because all we had to do was convert milliliters to liters and we were good to go. So now we're just going to continue to expand on the complexity of these problems. So again, you'll notice in the last line, it's asking to determine the molar concentration. So what's the first thing you should write down? C equals N over V. C equals N over V. And now go hunting for that information. Is there anything that we can put straight into there? I can do a conversion to liters, and I can put it right in the bottom. And that's excellent. We should be able to have that skill. I don't want you to write out all those steps that I just did to get the 0.25. So I want you to think, oh, milliliters, 1, 2, 3, 0.750 liters. We'll assume it's 3 significant digits. You could maybe think that it was 2, and it would be fine. What do I need to do next? Yep. Yeah, so I need a molar mass, turn it to moles, put the number in, and away I go. So we're started with a mass, so I need a molar mass for sodium hydroxide, NaOH, 1.0, 16.0, 23.0. I think that's a 40, isn't it? 40.0 grams per mole. 3.56 grams, 40. Looks like 3 significant digits. Now, do not clear your calculator. Bad habit, some of us clear. We don't just press it once. I'm a 4 clear. Clear, clear, clear. No, a 3. Clear, clear, clear. For some reason, you got to press the clear button a million times. You don't need to do that. What do we have for a number here? 0 decimal, sorry. 0.89. That's it? 0.0890. And that's moles. Now, the reason I say don't clear your calculator, because what do you have to do now, essentially, to finish this question? Divide it by 0.750. So get out of the habit of clearing your calculator every time you do a calculation, because very often that answer to that previous little calculation will roll right into the next one. And even if it's not, this one was easy because it's the answer you have divided by 0.750. But if you've got the answer button, you know what I'm talking about, second function answer. Some of them have an answer key. Even if it's divided by, you could put in your number divided by second function answer equals. It's a very useful thing to use. What do we have here for a number? We got a number? Anybody? Yep, cool. 0.119, 0.119 moles per liter. All right? Any questions or concerns? Okay. So now let's talk about how we can use that conversion, that molar concentration as a conversion factor. And we'll just go ahead with questions. Does anybody out there not have a calculator and is missing out on all the fun? Anyone missing on the fun? Oh, well, that's okay. I've got an extra one. I could tell you were missing out on the fun. Glancing left and right, looking at your friends using their calculators. Oh, that's fun. We actually don't need it in this case. But we can think about it for a moment, but we don't need it in this case because I'm looking to get moles, and you'll notice I'm not given a mass. So I don't need a molar mass. All right? And this is actually a good thing to discuss when looking at a problem that involves solutions. Now, we're going to be incorporating this type of conversion into our little stoichiometry steps a little later on in the unit. But I could make a little map for this. If I'm starting with 350 milliliters, and we already know that that number's no good because I have to have it in liters. So let's change it. What is this in liters? 0.350 liters. And if I want to convert that to moles, I'm just kind of making the downward part of the map. Now, there's no chemical reaction involved in this. I just have sodium hypochlorite. I've got so many liters, and I want to convert it into moles. The conversion factor is that molarity. And I suggest you write it in here, but when you do that, 1.3, change the units to moles per liter. All right? So when you see the capital M, a 1.3 molar solution, we're telling you the conversion factor. Now that's different than if we're converting with mass to moles. If I'm converting mass to moles, what do I need? I need the molar mass. Where do I get the molar mass from? What is that? the formula, which is why Cindy asked for the formula, right? Because she thought maybe we would need the molar mass. But we don't need a molar mass here. Now, the identity of the substance, sodium hypochlorite, gets us the molar mass. But for a solution, we really don't care what the substance is. The thing that tells us the conversion factor, this conversion factor itself, it must be given. It has to be given in the question. The person who determines the conversion factor involved in solutions is the chemist that made the solution itself. Depending on how much he put into that solution determines its concentration. And so I can have all kinds of different concentrations of sodium hypochlorite solution depending on how the chemist made it. Which means if I want to use the concentration as a conversion factor, the chemist who made the solution needs to tell me the information in the question. It's not dependent on the type of substance that I'm dealing with. Now, molar mass is dependent on the type of substance, but molar concentration is not dependent on the type of substance. It's dependent on who made the solution. And so the person who makes the solution or the person who makes the question has to tell us what that is. Okay, so now we're ready to go just like before. I have 0.350 liters of solution. I ultimately want to get moles of that substance. How am I going to put my conversion factor in? Where's it going to go? Where's everything going to go? Yep, cool. 1.3 moles on top, 1 liter on the bottom. Now this is also a little different than a molar mass. A molar mass, like 40 grams per 1 mole, you'll notice the 1 goes with moles because it's a mass of 1 mole. In a molar concentration, the number goes with moles and 1 goes with the liter. And that's because the molar concentration is defined as how many moles are in 1 liter. So there's a couple of little differences between a molar mass and a molar concentration. Okay? Does somebody have a number for this? As I'm babbling away here about the differences. Cool, I'm thinking does. What do you got? 0.455 moles. That's looking like 2 significant digits. So 0.46 moles of sodium hypochlorite. Okay? Now, if the question asks what mass is that, then I'd need a molar mass to finish it off. In this particular question, you'll notice it doesn't even mention what the substance is. It just says salt. Doesn't necessarily mean sodium chloride. It means any ionic compound. But I don't need to know the identity of the substance because in order to do the calculation, I need the concentration as a conversion factor, and whoever made the solution has put that in there for me. And that's all that matters, that I've got that. Again, if I was making a map, and this particular map was on a balanced chemical equation, if I started with moles, it would be at the bottom. In other words, I have 0.37 moles, and I want to work my way up to question mark liters, right? It's like I'm moving back up from the mole line. Now, this isn't a stoichiometry problem because this does not involve a chemical reaction. This is just a substance, and if I need to have 0.37 moles, what volume of that solution will I require in order to have that number of moles? Again, the conversion factor, 0.90, and again, turn the M into moles per liter. And now you've got all the tools you need to go from moles up to liters. 0.37 moles. I need to get rid of the moles. I need to put that on the bottom. The number goes with the moles and 1 goes with liters. 0.90 moles per 1 liter. Moles cancel out, and I have the volume of that solution needed. And it's looking like 2 significant digits all over the place. We'll take the number when you get it. And if you don't want to give it to me, that's right. We'll go to coal. That's correct. Michaela made a look back. Why would I put my hand up? Coal's just going to answer it right over here. And I used to care, but I don't so much anymore. Rachel, thank you. 0.41. 0.41 liters. And if our measuring device was in milliliters, how many milliliters would that be? Now, this isn't a big deal. I just want us to think if we can go backwards the other way. How many milliliters is this going to be? 410 milliliters. 410 milliliters. Not required, but just be able to do it. You'll notice sometimes I make the L big and sometimes I make the L little. Have anybody noticed that? Now, here's the issue with the term liters. You're going to get a little story out of this. When units are given symbols, if they're not named after a human being, the symbol is supposed to be lowercase. Now, I'm not talking about giga and mega, but I'm talking about meters. There was no Mr. Meter that invented the meter, all right? But if you're taking physics and you're going to talk about newtons, you're going to put it as a capital because there was a Mr. Newton. And there was James Watt, right? And there was James Prescott Joule, all right? But there was no Mr. Liter. But for some reason, we use the capital L to represent liters. And then when we put a milli in front of it, we like to get rid of that and just write it as a lowercase l. So it's really all over the place. Sometimes you'll see it like this. Sometimes you'll see it, you'll never see it just like this. Maybe you will sometimes, just a lowercase l. It should be lowercase l. There was no Mr. Liter. And I have searched online for a fictitious story that someone wrote describing about Mr. Liter. He was a Frenchman. He didn't exist. This is a fake story. He was a great glass blower, and he created these phenomenally accurate measuring devices that could measure volumes to great accuracy, and they paid homage to Mr. Liter. No such thing. There is no such. I don't even know the origin of the term liter. It is French, I'm sure, but there was no Mr. Liter. So I don't know. I put down whatever I feel like writing down at the time. Okay. So again, we're just kind of increasing the complexity of the problems. And you know what? I'm really hoping that we've done conversion factors enough that you're sitting back there going, okay, we get the idea. You string some conversion factors together. You cancel out some units and you're done. What are you spending so much time on it? And if that's the case, excellent. Then I've done my job. I also hope that every time you write down a conversion factor, you're thinking in your mind, what's the job of that conversion factor? To convert from the liters to moles, and then from the moles to mass, that they all have a specific job. The neat thing about it is, if you can learn how to string them together and not understand what they do, you can still get by. You can still get to the next course. And maybe by the next course, you'll figure out what it means. Survival. What mass of silver nitrate is needed to make 850 milliliters of 0.12 molar solution? Okay. So this becomes a little tricky because we've got to realize that this thing here is a conversion factor. That's the main important thing, that thing there is a conversion factor. That's not our starting number. That's not where we want to go. That's one of the numbers that are on our arrows that tells us how to get there. My starting number is 850 milliliters, which means we're starting with a volume. I'm making the map right here, 850 milliliters. Look, I got rid of the capital L. And I'm going to make my map go to the right because this is not like one of the maps we do in a chemical reaction because we're doing something else here. I eventually want to convert the milliliters of solution into mass, into grams. And there is no conversion factor that goes straight from milliliters to grams. But I can go from milliliters to, this is where you're going to help me out, to moles. And which conversion factor goes from milliliters to moles? The molarity, that thing right there. And that's where we're going to write down the 0.12, and we're going to write it now as moles per liter. Now we're ready to roll. And now I can go from moles to mass, and what does that? Molar mass, which means I need the formula for that thing. So I gather up my conversion factors, I string them in a row, and they're already talking numbers. That's exciting. Nobody wants to give me the answers, but Wes wants to share it with absolutely everyone around him. AgNO3, and come on, Wes, share it with me too. What'd you get? 169.9, 169.9 grams per mole. That means Wes is long done when I'm begging for answers, and he just stares at me. It's okay. I can handle it. You want me to work a little bit for my money? That's fine. I understand that. Okay. So we've got to get rid of that thing. 0.850 liters. My map is guiding the way. I need liters on the bottom. 1 liter, 0.12 moles. My liters are gone. I need to get rid of moles. For every mole, it is 169.9 grams. Oh, I know you've got it. I know you're staring at it. Do you have the answer? 17.3? 17.3 grams, just checking for significant digits. That could be 3, but our concentration is just 2, right? Because remember that point, that 0 is just a holder, right? It's just telling us where to start. So 17 grams AgNO3, and I hope it's right, because Wes will never give an answer up again if you got it wrong. Okay, so like I said, we can string them together. The concentration is a conversion factor. I've got one more. Hold on one second. What volume? Yeah, no, that's going to be the same one. I'm going to jump ahead to the last one right there. And this last one kind of links what we did yesterday to what we did today. And then I'll let you work. My goodness, 45 minutes of time, which means I'm going to have to be mean to some people again. But Dave's not here, which means it should run a little smoother. That's okay. Lots of time to practice means we can master it. That's what we want to do. So this is an entertaining one in that it has numbers that we saw yesterday, 15% weight/volume, which means we can get little bits of information out of this thing. And in the end, we want molar concentration. Well, if we go by what I told you to do, when it asks for molar concentration, what's the first thing we write down? Oh, that's good stuff. You had it. You were going to do it right, but he bailed on me. C equals N over V. C equals N over V. Now we're going to go hunting for that information. Well, let's first turn this thing into what we know how. What does that mean again? What does the 15% W/V? What's it going to get me? Cindy? 15 grams of the, you made me give it away. 15 grams of the solute. What is the solute in this case? What's being dissolved in this case? Yeah? Sodium hydroxide, 15 grams of NaOH. And the G comes from the W. And what goes on the bottom? Sorry? 100? 100 what? Milliliters from yesterday. Grams per milliliter. And that's of the entire solution. And if you forgot about that, you got to go back and review yesterday's stuff. That's yesterday's information. So now let's see if we've got any information now hidden in here that we can use in our C equals N over V. Do you see anything that we can maybe substitute in there? Yep. 15 grams on the top? No, I can't put 15 grams because what does this N stand for? Stands for moles. I can't put grams up there. So we got to do something, but is there anything else you think that we can just substitute in there? Is that a hand up, Carissa? Is fiddling with the pen? We're going to go with a hand up. Carissa, do you see anything here that I can put into this equation? This 15 grams is in 100 milliliters, so we can put 0.100 liters on the bottom. What do I need to do next? Carissa. Yep, using the molar mass of sodium hydroxide. And then we've got it. So we can easily do that. We just need to pick out the information that was in there. So 15 grams NaOH. I think we did NaOH earlier on. 40? 40? 40.0 grams, 1 mole. Don't clear your calculator. And then divide by 0.1. And it's looking like we're to 2 significant digits due to the 15 at the beginning. So I'll take the number of moles. Then Cameron, what do you got? 375, and that is moles. Now, this is 2 significant digits, but it's always a good plan to keep an extra one until you get to your final answer. So 0.375, 0.375 moles. And a neat little trick, when you divide by 0.1, it's the same as multiplying by 10. That's that little powers of 10 thing. And if you can, then you really don't need to run it through your calculator, because if you're multiplying by 10, it's going to be 3.75 rounded to 2, 3.8 moles per liter. All right? But you can run that through your calculator if you need to. Okay, so there is our introduction into molarity. You've got the bottom half of that page that you had yesterday. You've got lots of little practice problems. Practice makes perfect. I'm willing to give you 40 minutes to pound through as many of these as you can. If you have any problems or concerns, come on up and ask.